Hi, good afternoon, everyone. I hope my screen is visible. Can anyone please confirm? I'm audible? I'm audible
Yes,
now?
it is audible.
Okay. So, good afternoon, everyone. This is Ayush. I am an application engineer at Integrated Microsystem. In this session, I shall be focusing on the latest inclusion in Synopsys Simpleware software that is ultimately aimed for various pre-surgical planning and also post-operation outcomes that we can do using the tool. So without wasting the time, let me give a brief agenda about this presentation as well as the live demonstration of the software. So first of all, in the presentation part, I shall be starting with the basics of Synopsys Simpleware, how we have different tools that helps us in assisting and overcoming the challenges that we are present in the present surgical planning methods. Also, the role of automation in surgery and why we require such new inclusions coming on to the latest cases that we see. So, starting with Synopsys Simpleware software. So, it's a part of Synopsys range, which basically deals in medical image processing of dataset. Herein, we can import the dataset in the form of CT, MRI, micro CT, and not just that. Apart from this, we also have inclusion of any raw images, JPG, PNG, TIFF inclusion, which can be later on constructed into 3D reconstructible model. Why I have highlighted other methods is because, for example, if we are developing any implant or working on an implant, and we need to bring it in our view section to have its integration with image dataset. So there's a strong need that we have the support of various import formats, and that is an advantage in Simpleware. We are not just limited to any DICOM format or any STL format. We have coverage of all the raw image dataset files. Apart from that, any volume mesh file, CDP, INP is also being supported. So that helps us in generating end-to-end workflow. We can have the integration with the implant data set. We can do the virtual X-ray generation to check whether the positioning is proper or not, or even if there is a minute mistake in our segmentation, that also can be checked using a dice score calculation or overlapping the particular mask that has been created with the volume rendering of the dataset. It's applicable in a wider range of applications because we not only just cater to the medical applications, but it also has its advantage in any sort of material reverse engineering. But since this particular session is much more focused on the medical aspects of the tool, I shall be focusing on that. And what all are the tools that are using in medical image processing? The same tools are basically used for any material research also. So we have the full coverage within our simpleware range. Now, first of all, let me highlight with some of the problems or what are the challenges that we have in the traditional surgery plan. When we encounter with the conventional surgical planning, what the doctor has is he has a 2D scan view of any data set, either being X-ray or even if the doctor is having the CT data, MRI data set. That is not very clear when we see the data set in 2D because when we are converting any 3D data into 2D, we might not get a great perspective of what all work that we are doing. Also, there might be some error while we are generating the output depending on the 2D view and the particular work that is to be done on the surgical table is in the 3D. So that encounters an human error and a variability in planning basically. So to cover that, we have this new software solution like Simpleware to overcome the requirement. We can do the 3D reconstruction of the model if required in some of the complex cases. If we are not yet satisfied with the generated output, we can also do the 3D printing of the same. This helps us in basically reducing down any mortality rate. Also, it increases the particular surgery success rate ultimately, and which is our ultimate aim to save a patient's life. So while integrating any digital workflow, it definitely helps our specific requirement and reduces the time of computation too. Now, there's basically uh, need to understand how the automation process works. What is the workflow that is being used behind that? So the first part is the image processing. In the image processing part, we have three modes of segmentation: the manual segmentation, the semi-automated segmentation, and the fully automated segmentation. Before that, in the image processing, there are also certain fields that need to be considered on. Like if our data has too many noises, so we are being supported with various noise removal tools. We can use any Gaussian filter, we can use our mean filter to reduce down the noises. But sometimes these filter might also cause distortion in our images. Distortion in sense if it is removing any small element. So if there are any other small feature that is being present, that also might get removed. So we need to have a proper overview of our image data set that we are working on to have a very clear perspective of the same. Now moving on to the segmentation part. In the segmentation, what general workflow that we offer is, we say just do automated segmentation using simple web. And even if your data doesn't get fully automatically segmented, what we have is we are being supported with semi-automated too. So while generating an automated segmentation, we might get a perspective about what are the different areas in the anatomy. And if some features are missing, that might get covered using automated segmentation. And later on, enhancements can be done in the automated segmented result generated output. So since we are not much relied on the conventional sheets to work on each and every slice individually and to do the 3D reconstruction, because it might take hours and hours of time just to do the segmentation and coming on to the 3D printing part, or if we are doing any research to develop any FEA model, CFD model, it might take much more time. So it's generally advisable to do the automated segmentation and later on do the remaining process using semi-automated segmentation, and it will reduce down our work time to around 15-20 minutes to any difficult anatomy that you are working on. Sometimes for any specific cardiovascular cases, we might take a slight more time, but that is justifiable if we need to achieve a good accuracy in the segmentation, because how good the segmentation is, it ultimately basically says about our result that we're working. So, for example, if we need a 3D printed model, so we need to have a proper segmentation of the same, uh, the particular model that we are working on. And once the segmentation is done, we move on to the next part, that is model generation. Basically, there are four types of model generation capabilities. The first one being the finite element model generation, the second one being computational fluid dynamics model generation, the third one being nurse model generation, and the fourth one being the surface model generation. Why we highlighted all the particular model generation? Depending on our task to task, we sometimes might require any type of FE model creation if we need to do analysis and check wear and tear of any implant over a period of time with the particular image anatomy that you are working on, or for cardiovascular cases or any hemodynamics cases, we might require a CFD model to check for the blood flow, to check for any respiratory system. We might require a CFD model generation. For doing the direct 3D printing of an anatomy, we can convert it into a surface model. And sometimes if we require high quality CAD files like any NURBS file, so we can do the export in any step format or IGS format as desired. And once this model generation is done, we also do provide with some of the computational capabilities like particle analysis and pore analysis, and another central line network tool to analyze whole set of any center line that you need to work on. We can check for any set of cross section. We can check for the wall thickness. Then there are a couple of other tools in the measurement, like point to point measurement, angle measurement, dihetal measurement, that we can cater to. So these are all being covered in simple way. Now, moving on to the next part is the automated segmentation capabilities. In our software, the segmentation algorithm that we use are pre-trained neural networks. So to segment out any orthopedics part, we have a good coverage. And we also have certain new inclusions such as a external model capability. So even if we are developing our own set of segmentation algorithm, and we need to cross verify whether our segmented algorithm is how our segmented algorithm is working, how is the output comparison between our set of algorithm and the automated segment algorithm from simple way. that all can be completed out in a single tool, that is simple way. Here, as you can see right now in the screen, the automated segmentation tab has ankle CT, knee CT, knee MRI, hip CT. Also, if we need to do post operation revision of any hip CT dataset, that too is also supported in the latest release. And then we have the spine CT, CMF CT, heart CT, and heart valve analysis. Whenever we are considering a spine CT dataset, what we will do is we'll just provide a CT dataset over here, and here we have two additional options. One is the keep all bone fragments. So even if we have any trauma data set with us, it will do the segmentation for us, and it will basically work on the principle of grayscale range. So if it identifies some of the fragments of bone that has similar grayscale range, it will do the identification and do the segmentation task for us. Next is let us switch on to the live demonstration one such case. So how the automated segmentation algorithm is working. So I'm just opening the simple software. It will hardly take 1 minute to basically turn on. And once it is done, we have the particular view range. So we have various toolboxes which supports our workflow. Then all the image information is over here. Then how to import any data set, we can check over here. If we are working on any existing project, we can load it from here. And then we have the help and support section. These all tools I'll just cover up in the upcoming slides, how we are doing the import, how we are doing the export. Just to show how the automated segmentation work is, I'll just scan a folder that has the particular library of pelvis CT data set. So I'll just hover on. So I'll go to the selected folder, nostril, medical. So we do provide with a sample database library to start our work with and ultimately get familiar with the tools to play around. Here, whenever we import any data set, we can see the total number of slices being present. So starting from 1 to 279, so there are total 279 slices. All the DICOM text information can be checked from here, and to preserve the confidentiality of the data, we can anonymize this particular DICOM data text from here. Once it is done, we'll just click on selection. Now, when we have obtained the data set, we get the common coronal view, sagittal view, and the axial view. And over the right hand bottom side, we have the particular volume rendering of any data set that can in which the presets can be changed. So even if we need to visualize any difficult set of anatomy, so there are numerous anatomical presets that we can use. For example, it is a bone, so I can use a bone. If we are working on any cardiac data set, we can select the following preset. If we need to check the highlight the coronary arteries, we can do the same. Or even if there are any sort of airways that being present, so we can use the MIP range. So there are multiple options that we can use. So selecting on the preset as a bone preset, we can check the data set, how this data set is looking. And we can see there are a lot of small number of filings that being present in the data set. So when we are considering the semi-automated segmentation, so we need to use various sets of methods to remove this island. But since I'm just showcasing how the automated segmentation would work, I'll go over here, the Precision CT, keep this particular, keep all bone fragments, output femur, and fused bone. I'll be just applying. Right now it's around 470, and it will hardly take 2 minutes to do the segmentation. So let us wait for the output to be generated, and later on shift to the next slide. Why I have shown this automatic segmentation? In certain cases, the data may not be at all proper. So there might not be a particular good output that is to be generated. So what we'll do in such cases, in such cases, we'll focus on individual parts, do the highlighting, and later on do the operations like smart paint operation or a multi-level or two segmentation, and then identify the different regions that being present. Also, there is one more inclusion that wasn't present in this particular slide, being the external model. So you can see this version was 2024.06, and the current release that has been released in this month of June is the 2025.06 that I am presently using. And it has this new inclusion that is external model. So even if we need to use the UNet model from NVIDIA, Monet model, that can be used for a total segmenter from 3D slicer is also now being supported. So we can see the process was started at 417 and it's now 419 and the auto segmentation is completely done. Now it has done the segmentation for us and if we require to only work on a specific part, we can isolate that out. So we can see how fast segmentation is and how good is the accuracy in the case of prosthetics. So moving on to the next slide is the particular patient-specific model creation. This is also one such application area that we generally use SimpleWare for. So as you can see the output that I have generated using automated segmentation. But there may be a question. Someone might ask me, so why we are generating this model and what is our ultimate need to generate such model? So one such need is this sort of a model creation. So the particular patient has a ventricular septal defect. So the particular patient had a VSC defect, and what we did was we created a heart blood model, and later on divided into four sections. So let me magnify this fusion. Yeah. So we had developed a four-sectional model, and once this particular sectional model was created out, we had given it to surgeon to do the particular pre-surgical planning, to plan out how to conduct the surgery. So this is one such application area that is being used, especially in the case of complex cardiac cases. And it reduces the risk in the operation by significant margin. We can create such models in a time less than 5 minutes. We can do the automatic segmentation and generate out the output for the same. And later on, it can be exported into the formats like 3MF, STL, OBJ, whichever is required by us. Also, what all segmentation output that we are generating, we can also export it to VR file. So we can visualize a particular VRML file and any VR viewer, and we can check out the segmented output result from the same. Now, as discussed in the previous slide, the export models to be supported. Even if we are working on any design, we need to do certain modifications. So this is one such device that is being used in the case of Unilogy that we have basically checked in SimpleWare about the design. There were certain feature corrections that were required that was done, and the output that we got was significantly high because what we had done is we had exported out it as a FE model, and then the particular export format that was selected was a STL file. So the number of triangles were around 5 to 6 lakh in just a small piece, and the output accuracy was much more higher. So the tolerance value also got decreased to 0.2 millimeters. So this way, we can have high quality volume mesh files to be directly created. And later on, depending on our work to work, we can export it for FE or CFD, or even if we need to import any DICOM data set from text server and do the work accordingly. So that can also be done. We have a wide range of image modality support. To cross verify it, let me open another window of SimpleWare. Yeah. So coming on to the import and export format type. So once we are doing the import, you can see we have the majority of the coverage like CT, MRI, micro CT. Also, any 4D image data set if we need to work on, that can also be worked on too. So we can scan any photo containing MRI, CT, micro CT, 4D image data set, and it will highlight the particular image data set. Then we also have any industrial image data set that is required for non-destructive evaluation. So the particular folder can be scanned and the image data set can be loaded. Now, having the PAC server connectivity. So if any hospital wants to directly connect it using a PAC server, that can be done. This way, the confidentiality of the data set can be kept out at top priority. We can have the password set. So if we need to do a password protected password, that too can be done. Now coming on to the best part is this second raw images support. So you can see there are a large number of image modalities that we support like BMP, JPG, then TIFF, raw image, volume image, and many any format that we need to work on. We can do that over here. But the advantage part that we have is we can set out the individual spacing over here. So we are having a large data set supposedly of 5 GB, 4 GB, and we need to reduce down the data set directly even when we haven't worked in the 3D or the 2D view. We can do that by reducing down, by increasing the spacing, so it will reduce down the data set size. So that is one such option that we can do regarding the import. Then we have the 3D image import format like HDR, HPM, Enterprise, then Nifty images are also supported. And last, we have the STL and CAT format. So even if we need to support any STL CAT file, STL, CLY, IGS stuff, that can also be imported too. Anyone has any question? So apart from this, we also have one volume mesh file support. So even if we are importing any CTP answers, Abacus, BTK file, that too can be carried out in a very efficient way. Now, this being the import format. Now, someone might ask, what are the export formats that are being supported? So when we are working on any project, for example, let me open this particular auto segmented data. When we move on to export, so this is just the export type that we support for the DICOM images. We haven't done any specific operation. We have just done a masking. So what all are the export formats that we support? So we can export the particular data as background raw data set, then background meta image data set, then background to stack of images. If we need to convert it into DICOM, that can be done. If we need to export it to back to text server, that can be done. Any scene to be exported out into 3D PDF can be carried out, and then Nifty image export is also supported, and DICOM encapsulation can also be done. So these all are the export format that is just being supported for the mask that has been created. Now, we are not just limited to these many export format support. When we will be developing any model, we will be again getting multiple export formats to be supported. So we have, when we are developing any surface model, we have the export format as PML, Abacus, ANSYS, ANSYS Discovery, ITS, MATLAB, Open Inventor, Point Cloud, Polygon file format, STL for 3D printing, VRML, and Wavefront. So this is just for surface part. And when we will be developing any finite element model, we can directly do the particular catching model creation for any supported software like ANSYS, Abacus, COMSOL, LS Dynam, MATLAB, Nastran, Pattern, BTK. And once this particular exporting is done, we can later on, we don't really require to demesh the particular surface in any of the files. So this is done. Then for the CFD, we have the support of VTK, then OpenFOAM, COMSOL, Fluent, LS Dynam. And last but not least, for now, we have IGS and step file support to be exported out. And coming on to this modeling, so we have a wide range of parameters can be varied out. We can set out the coarseness level individually, fineness level individually, corresponding to each and every mask. So if we require a coarser for some region and finer mesh for another region, that can be done from here. Similarly, adding any contact points, node points, shared, shells, mesh point. These are all the tasks to be carried out directly in FE modeling range. Now, this was the export model types that we support. Moving on to the next slide is how we are working on in a orthopedic scale. So this is one such HIP model that I have taken the case study that we from SimpleWare, right? What they had done is they had done a post-operative surgical planning of this hip acetabular cab implant design. So the particular 3D imaging was done and a virtual code model was created using the automated segmentation. And this result was generated in less than 1 minute. You can check the relative accuracy of my wordings on the Synopsys Simple website. They have listed all the data sets and done the publications directly. So the particular details that I mentioned can be cross-verified over there. Then once this particular virtual report model was done, all the implants that were pre-existing were identified. There was a requirement of generating a fresh implant to change the old acetabular crab implant, and once this was done using freeform, we had done the attachment and placed the particular positioning accordingly. And once it was done, it has streamlined the process and reduced the turnaround time by significant margin. Here is one such more example of a spine, uh, spine surgical planning. So this is how the automated segmentation was carried out, then designing the implant, setting out pins and drill holes, and later on developing out the implant accordingly. So let me just show how any surgical cutting guide works in simple way. Since this was the segmented data set that we were working, it will be much more easier to directly show how the particular surgical cutting guide works. So to go, we go over to the surface tool option. Here we have a dataset conversion tab. Selecting on this master surface, we can select the particular part that we are working on, selecting it as hip right, clicking on generate surface. Before that, every time we see a window of out of date, we need to click over here to generate a fast preview. Once it is done, we generate a fast preview, selecting out the surface, and just created out a surface. Now to create a surgical cutting guide, it is a very easy process and simple way. Then we will be going on to the 3D printing tool tab. We will be getting multiple options. Over there, one such option is the design tools. There is the option of create cutting guide. Once we have selected this particular part out, we will be selecting on add guide, selecting out multiple planes, clicking on yes. Now we just need to select out the point. So for example, if we need to create a cutting guide over this region, we will be selecting out the plane accordingly. And once the plane has been selected, we can cross verify it over here. The next task is to set out the pin center rules. And while we are setting out this track, we can also change the dimensions from here. So you can see once we do this particular modifications to check the particular track height, we can review the track that we will be working on. And once it is done, I just cancel this operation for now to showcase the whole operation at once. We will be selecting one next task to set in center rule. So we can set out the full radius accordingly, wall width, the height of the pins that are being required. Once this is done, we can set out the points like this. So like this will set out the points. And once this is done, our next task is to set out the base for generating a cutting height over the existing surface. So we will click on this brush. We can increase the dimension according to the specific requirement. We can increase the brush height if required. So just to highlight this function. And one more advantage that we get is whenever we are placing a pin out with hole, so it will always be perpendicular to surface at any point. So even if we need to cover out the specific part, we need not to worry about its accuracy. Once this particular base has been selected out, we just need to click on preview to check even whether the particular copying guide that we have created is accurate or not, or if we require any modifications to be done that can be carried out for the same. Yeah. So once it is done, we are satisfied with it. We can just click on save, and now we can visualize the particular cutting guide that has been created out. This is a major step that has been included in Sample to reduce the cutting guide feature. So even if we need to work on specific cutting guide, if we need to create on the existing surface, if we need to do the mirroring and all, that can be done seamlessly on Simple There. We can just highlight the particular part that needs to be mirrored, and then various operations can be carried out. So it takes around 1 to 2 minutes for the cutting guide to be created. And once the particular process has been done, If a particular step is about to complete, it takes around 30 seconds, maybe 30 seconds for the cutting guide to be created. And this is how we can create any cutting guide for the success. So if we are, even if we are doing a cranial maxillofacial, working on any cranial maxillofacial defect, that can be used also in the process is quite seamless. That we work on. Once it is done, we can also isolate the particular surface that we had created and all can be resolved in a single case operation. And if we have any surface deformity, so we have the inspection tool to check the printability of the cutting guide, to check and fix the particular surface, if there are any sort of errors to the system. Once it is done, the operation click over there and now you just click on the create surface option. Meanwhile, let the process to complete. So this is how we can create any cutting guide directly. Moving on to the next part is the integrability of simpleware with any implant design tool like SolidWorks. So it's a quite simple process that we have over here. What we need to do is we need to go the surface section and in the same surface section, once the particular this process is complete, we will go to the surface tool option. And in the surface tool option, we can import surface of any type. So any SQL OBJ file can be directly brought in simple way, and then it can be planted and positioned accordingly. So if we need to do the modifications in the 2D view or the 3D view or the 3D view, whichever is required for a specific set of workflow, that can be carried out. So let me show my part first. Click on this. So it's lagging. So whenever we are importing any surface file, we need to click on this import surface. In the same example dataset library, I do have an applicable implant SQL file. If I need to just import the particular surface file, I'll click over here, clicking on open. And once I open any SQL file, all the important information, the total number of polygon count, the total number of points, whether the particular file, but particular file that you're working on is watertight or not can be checked from a are any cells intersections being present can be checked from a whether it has any bad orientation can be checked from it. And if all the particular problem is all the particular surface is perfectly fine, we can directly click on import. Or if we have any problem, we have actually a click option known as switch to correct out all the surface import issues that we have. We can also set out the particular scaling accordingly if we need to change the scaling. That too can be done. Once we have imported the particular SQL file in our view, first task is to bring that out at origin position. To do that, we click on the zero position tab, selecting this surface as an active surface. Clicking on apply, it will bring it at origin position, that is 0, 0, 0, corresponding to XYZ value. Once it is done, our next task is to do the position. So some might be familiar with the positioning in the 2D view, so we do have the support over here. And we will always see whatever task that we would be doing for 2D and 3D view. So for example, if we do the particular modification in any of the views, we can see the resulting changes in the other view. So this way the positioning and orientation is very accessible for us. We can also do the same changes in the 3D view. So we just be facing out the vectors accordingly, which are which required for one specific set of workflow. Once it is done, we'll be rotating over here, like over here, and a little bit over here. Once it is done, we have imported the STL file. We have worked on this particular data set. It's the data set over here. And once we are satisfied with the positioning of the particular surface, we just need to click over apply, and it will select out the specific part and do the positioning accordingly. So the particular file that we have created, the HTTP positioning can also be checked out in the 2D view or the 3D view. You can check the 3D object contours whether the particular fitting is proper or not, or if there is any modify the changes slightly over here. We can change the orientation directly in decimals so that we achieve the accuracy at the highest possible value. This is how the surface tool tab would work. And then moving on to the screen printing, because sometimes when we have created an implant, we need to also create connections between the implant surface and the existing anatomical surface that we have segmented out. To do that, we have two options. First is to directly create connectors between them. So we can set out over here, we can select the surface that we require the connectors for. And then we also have an automatic connector generation settings over here. We can select over here. And what all connectors would be possible for the existing surface that we would be working, it will create that automatically, and then we just need to click over here and see, you can see the particular connectors and create it automatically. So in some cases we also might not require some of the connectors, so that will be trimmed out directly, or else we can also remove that connectors from here. We can delete the particular part. One more thing that we can do is we can reduce the opacity over here to check whether the connectors are proper or not. We can reduce the opacity of this right as well. So once it is done, we can see the connector positioning, how it can attach to the surface, and sometimes we might also require is to just do the partitioning into two different surfaces. To do that, let me go over here, and for example, if I need to do a cut plane creation over this particular part, what I'll do is I'll click on this partition and symbol. I can directly select out any plane along which I need to do the partitioning. And once it is done, we just need to click on apply. It will separate out these two surfaces individually. And now if we need to do any pins and socket creation. So this is not just limited to this part. It is very much beneficial when we are working with an ECMF dataset to create out a clip surface plane and later on do the pins and holes positioning. So we can directly set out the radius over here 2 millimeters, then 5 millimeters, again 2 millimeters. So whichever is the pin radius that is required, we can set it over here. And then once we are finished with our work, we can just click on create, and you will be seeing that over the one end it will be creating the particular pins, and over the other hand it will be creating out the holes. So that can be checked from here. If we just isolate this particular part out, we can check that it has created pins over here. So we might also not require any sort of magnets to connect the surfaces. When we have a pins and socket connection, it will automatically uh, get connected directly. Also, whenever we are working on first surfaces, there is also need to check the printability of the surface. So we have two options. We can do the color grouping also if we require, and we have multiple parts. We can check the printability from here. It will generate a option of the wall thickness along the surface, whether all wall thickness is proper or not. We will be seeing out the surface information, the total number of polygons the particular surface is having. We can also annotate minimum and maximum and enable rules. So at corresponding to what point we have the minimum wall thickness, corresponding to which point we have the maximum wall thickness, we can check the particular surface from here. And then we also have an option of check and fix. So if there are any sort of surface error that being present, we can check from here. We can fix the particular surface error directly and do a set of tasks. And once we have completed this, we can directly export out to the screen that we are working on into any TMS file, STL file, OBJ, VRML, PTPTS. So these are the multiple image formats that we can export once we have done this use case of this cutting tool, then partitioning tool, or a cutting guide creation. So these are the advantages that we have. And we also have a direct link up with SolidWorks. So if we have an active license of SolidWorks with us, so here you can see we have a design link model. We will be linking in this current system that I'm using. I don't have an active license of SolidWorks, but just how the particular tool works is we will be linking up SolidWorks with Simpleware. Later on, the particular file can be brought in any of the format SLD part or SLD ASM. And once the particular files have been imported in, we can later on do the particular all the positioning. Also, whatever modifications we will be doing in Simpleware can be visible in SolidWorks and vice versa is also true. So we need not to do the import and export again and again. If we have the two different tools, we can just use the designing tool to integrate it as well. And later on, we have multiple other options also. We can group circles, we can ungroup, we can also set in the internal lattice structure to reduce down the weight of any part that we are working. For example, if I need to have an internal structure wizard creation, I can select a particular part. We can select out the cell type, whichever is required, selecting the cell launching, and this is how our internal structure would look. Once it is done, it create out over here. Since this was the active part for which the mask has been created, this is how the active structure is created. We can see how the internal structure will look for the active circle. We can reduce down all the particular values in terms of dimension over here, and we can check and correct the surface accordingly. So this is how our tool works while linking up SolidWorks or any other plant design tool. Now, in certain cases, we also might require a particular output to be generated for finite element analysis simulations to test the particular surgical scenarios into virtual environment for the creation of work. So what we do in such cases is we go over here, whatever surface, let me delete this for surface for now. And as I have mentioned earlier, that we have a dedicated setup model tab. So we will be selecting out the model as a model. We will be selecting out the regions that I require. For example, let me just take the hip part. I will remove this pencil schema, accept. And here we are given with two sets of different algorithms. So we have the FE grid algorithm and FE free algorithm. In the FE grid algorithm, it works uniformly for whole surface and it has a similar value of triangulated surface across the region. In the FE3 method, in certain areas it might have a tensor meshing, in certain areas it might have a coarser mesh as required. So it will automatically select out the algorithms. We can also select the element type as alt-iterate, linear, quadratic, classic curve edges, straight edges, or we can also have the element type to be mixed iterator or iterator. Then setting out the material properties, we can set it on the basis of grayscale values. We just need to set out the grayscale range, and once it is done, we can set out the Young's modulus and Poisson's ratio. Take the definition so that the particular material can be later on. So for example, if I have defined the particular Young's modulus and Poisson's ratio value for a hip right, and I need to use the same data set working on a similar case, it will be all saved in the load material library, and we can select the load selected material. It will go the material accordingly. Now, for clicking on adding all the particular possible contact pairs, it will add the particular region. Or else, if we need to work on this hip right and femur right, what we will do is I'll just drag and drop this particular two options. And now, for example, if I need to set out a boundary condition for this particular specific region of interest, so what I'll do is I'll set out the contact points, add manage region of interest, and then we are given the different types. So we can use a system, or we can use primitive shapes, or we can directly select out the whole map. In this particular period project, so it would be the most accurate tool to be used to set out the particular boundary condition, since the shape of femoral head is ellipsoidal in shape. Once it is done, we will click on done. Now, when we add all the particular contact squares, we can just select out the regions that are required in this content, and we can see we have got the particular region boundary between hip right, then the region of interest that we have selected according to the ellipsoid. Similarly, adding all possible set is now inclusion over here. We can select out all the particular possible sets. We can add any sort of shell. We can do the mesh assignment over here. Boundary layer settings can be done. And once this all is done, we can either check the model preview whether it has any deformity or not. We can check out the segmentation quality. And once we are satisfied with the surface, um, and if the surface is working for us, we can directly do the export in whatever file type that we have selected while we were setting up the model. So we are given with a greater approach while dealing in any sort of data set work that is being required. So this is how the particular FE modeling tab works. Apart from this particular normal analysis, we also have certain additional tools like inbuilt pore analysis, a particle analysis, or a fiber analysis that we need to conduct in. And in the measurement, we have a central line network analysis and the ball thickness too. So just it will take around 22 minutes for the process to complete. I will be switching on to the part of other analytical tools that we have. Yes. So once this particular finite element modeling has been done, and see the particular FEA model created surface. Now when we will be clicking on the surface option, since in the site of model we have selected an Abacus IMP file, it will automatically create out the same, and now we can select out the folder that we require, and it will automatically save that particular surface for us. Now we also we will get a full summary of whatever switches that we have worked on. We can check it over here, and we can also directly import the particular file. To know how we can integrate different software, we have a dedicated tutorial guide to learn about it too in a very detailed way. We can check from here. We can go over each and every task. For example, if we need to do any mesh refinement, how to use the mesh refinement. What is the algorithm that is being used behind mesh refinement that can be calculated out? Any sort of faultiness analysis can be done directly. Then any 4D image support can be checked from here. Image processing can be carried out from here. And the part that I was showcasing is if we search for an analysis workbench, it will showcase us how the particular, when we have created the particular CDB or IMP file, how to do the importing as the software, what all are the settings that being required. So it is a very detailed, uh, intuitive GUI that we get in this tutorial guide. So tell us about each and every part. We can also move into the specific part that is required. And once this all is done, we can do the analysis and later on import the same file in simpleware for report generation. Now coming on to the analysis part, since we have generated a FA model, we can do a pore analysis over here. We just need to select the diagram corresponding to which we need to do the pore analysis. Selecting on sensitivity, minimum pore volume, we will just click on this run analysis. It will take around 1 minute of time to generate out the analytical report. Once it is done, we can select out over here in statistics. We can check out pole values. We can also do a plot generation in which we can select different plot types. So if we need to check the pore elongation histogram, that can be checked. Then throughout eccentricity histogram can also be selected, or any specific solution that can be selected and updated from here. And later on, the same updated result can be exported. So we can do the export in the form of PNG file, or even if you need to do the export in a CSV or text file, that too is also supported. We will just click over here in the CSV or text file option is been created, and it will tabulate all the results that we have produced. So this way is how the analysis works for any pole. Similarly, we need to do a central line network analysis. Just taking an example of a femur right. I'll click over here. Once we click on create, we have this centralized network tool to be working. And once it is done, corresponding to any cross section, we can do the measurement directly. So selecting the point over here, we will get the plane normal value, point coordinates value, the area, the perimeter, the axis circle. We can check out the values accordingly from here. And we can also do the quick line statistic calculation. So we need to check the cross section area from here, the minimum cross section area, the maximum cross section area. We can have all particular sets of results over here. There are numerous options that we can calculate from here. We can also generate a report. To generate any report, we can go over to statistic template, load the selected template, and all the information that is being carried out as we're working. We can check from here all the voxel count, voxel volume, voxel surface area, mean grayscale, and standard deviation of grayscale. And here, even if we need to select out any individual mask, so the properties can be varied. We can also change any template according to our specific requirement by going into the edit section. And what all tasks that we have done, that's recorded in the log section. So if we need to have a part by script creation in a form of C sharp or Python file, we can select the particular part, we can choose convert, and we can create our own set of API. So this is one such advantage that we get. Now the next part that we have, the next part that we have over here is the end-to-end process. So in this particular, as I already showed how we bring in the particular CT data set and do the particular modification, and later on do the exporting out uh, in any specific desired format. Now just to do the recap of what all operations that we have done. So we have used a very simple workflow while we are using SimpleJet. We bring in the dataset to the image processing, and once the image processing is done, if a particular patient requires a implant to be designed, we use the help of SolidWorks or any other design tool, create out the implants, do the positioning, use Boolean operations to have the 3D printing done, correct out the surface, and do the pre-operative planning. Same can be done for any post-surgical operation planning. If we have done the surgery already, we can check for literal accuracy. So we can again bring in the CT data set that already has implant pre-position. And later on, during the image processing, FA model creation, we can check how long it will take for the implant to be wear and tear. So this way, it ultimately increases the whole surgical accuracy. And one more option while you are discussing this automated approaches, the time that it generally takes. So it might take around 6 to 8 hours per case while we are using the manual operation. The 6 to 8 hours is a full time to develop terms and also to design it accordingly to do the modification. And using this automated approach, since the segmentation has time has been brought down to 2 to 5 minutes, so it has ultimately reduced out our overall turnaround time. And it has also increased our consistency. Since in some cases, let me show for the same set of data set for which we have done the automatic segmentation. Let me highlight whole region. Now carrying out, now if I need to carry out a semi-automatic segmentation, it's generally easier for us since we have only worked with medical image processing. We can also use a C2 preset. Once this preset has been selected out, we'll be selecting over here, depending on the silent. Meanwhile, let me just isolate the particular semi-automated segmentation now. So this is how the semi-automated segmentation would look. It's the subsurface. It requires a lot of finishing that needs to be done. We can also overlap it with the volume rendering to check for the accuracy of the segmentation. Now, to further split it down, In the semi-automatic segmentation, we also require the splitting operation to be performed in. We will be selecting out the parts, moving on to the model slide to and then selecting out the different parts that we have. For example, we need to set out the boundary conditions properly over here and then over here. Similarly, we will be selecting out the left framework directly from here, right framework from there, that hip right over here, and then the sacrum over this side. So once this has been selected out, either we can check for a preview whether we have marked the particular boundary. This it's a demonstration file. We just clicking on the apply operation and to show how the dice score principle works. Uh, since we already require the streamer right, I'll just isolate it out. Now I'll apply certain operations to smooth out the particular surface. Operations like smoothing filter or recursive Gaussian or smart match with input work fine. Let me know the SR value down confirm to applying the operation. I think that I'll check it as streamer. And you can see it has done the smoothing, but it has also created some pulls and gaps. To cover this, we also have a single click operation that is bone filling. Clicking on this, apply it will again take 1 to 2 minutes of time to do the solidification of the bone. And once this solidified bone that we get, we can again apply for various types of operation like smart paint to further smooth out the surface if any part is still missing. And once that is done, I showcase the dice score in the measurement, how we can check for the accuracy of the AI-enabled segmentation versus the manual segmentation that we get. So once it is done, it has solidified the particular bone part. Now moving on to this measurement, we get into the mass simulator calculator. So this is the AI generated output and this is the manual generated output. So I'll select this. So the accuracy is around 91%. So it's a less accurate model. You can also overlap it with the city volume rendering final to check how the accuracy is ranging. So if I go over here, I can see how the accuracy is there of the automatic segmented generated model. So it's very much accurate, around 98 to 99% accurate model that we get from this automatic segmentation algorithm. This is how our segmentation platform works. Now, moving on to the next part. One more thing that one might ask whether we have the free trial or evaluation version. Yes, we do have an evaluation copy. It is a 30-day free trial period that we offer with SimpleWare. So anyone can go over to the SimpleWare website and later on check out the free trial option that we have. And apart from this, we also regularly keep on organizing such webinars on hands-on training sessions in between for our users to get familiarized with the tool and have an impact in the uh, surgical field, so surgical pre-operative field, post-operative field. So they can have a greater impact by using the high-end tools like Nokia SimpleWare. So the active future roadmap that we have is AI-enabled segmentation for soft tissue and vascular segmentation. Since majority of my part was concerned with the semi-automated, the fully automated segmentation for orthopedic part, but we do have automated segmentation for cardiovascular data set, which is very much needed because when we are dealing with any soft tissue, it's much more difficult to work on that data set. And later on, when we are even if we are working with any of the data set of soft tissue, we might not produce much accurate result. So I think I do have one example of the semi-automated segmentation that I recently done for cardiac data set. The particular patient had a VH data set, and the segmentation time that required using the semi-automated segmentation was around 30 minutes using the semi-automated tool, and using the automated segmentation, the segmentation took around 4 minutes. But some parts were missing in automatic segmentation, so the ultimate written model was obtained in around 15 to 20 minutes that we have to the cost of packing kit models that we had. Since it was a 4D city data set, we can also have a frame by frame visualization to mimic the beating of heart over here. We will just click on this frame toolbox. So whenever we are providing with a whenever we are providing with a 4D data set, we can also generate a live 4D preview of the same. This is just yeah. So like this, even if we need to mimic the beating of heart, that can be done according to different time frames, and later on the achieved accuracy is a very high accurate model that we get. So this is just a basics how we can use the simpleware in various surgical planning. If anyone has any question, they can kindly unmute their mic or also type in the questions in the chat box. So does anyone have any question? Uh, Even after this session, if anyone has any queries, you can visit our site www.india.org or also mail their queries at info@time. I'm also typing in my contact details in the chat box. So if anyone wants to have a chat or discuss regarding simple there, they can contact me over there. Sending in email ID. So after this session, I shall be mailing you all a feedback form. Kindly fill out the feedback form and let us know how or whether webinar was of any use to you. Also, in future, what are the specific topics that you would like to see in the upcoming webinars? So, if anyone has any query, they can unmute your mic and ask. Otherwise, we can end this session. So I have shared my contact details in the chat box. If anyone wants to contact, you can contact over there. My email ID and my WhatsApp as well as calling number. So thank you all for joining. Thank you for attending the session. Have a great day.